Welcome to another mini lecture for Module 6 on hypothesis testing and one-sample designs. In a one-sample t-test, we're often interested in comparing the mean from a sampled population, here represented as mu1, to a population mean that's proposed in the null hypothesis. And the test statistic for this is to calculate t, where we have estimated the population mean for population mu sub 1 as x bar, and then we're comparing that to the population mean that's proposed in the null hypothesis to that value, which is mu 0, and we divide that by the standard error of the mean from the sample. The assumptions for one-sample t-test is that data are a random sample from the population and that the variable is normally distributed in the population. And you can test this often by looking at histograms, and there's also some more sophisticated techniques for looking at normality. So an example we're going to go through for a one-sample t-test is that the literature says that the human body temperature is 98.6 degrees Fahrenheit, and we can ask the question of how well is this actually supported by data. And recall that there's 4 different steps when we're doing null hypothesis testing. So the first step is actually to construct our statistical hypothesis, and that is saying that the population mean is equal to 98.6 or that it's not equal to 98.6 degrees Fahrenheit. So that was step 1, is to establish our statistical hypotheses, is that the population mean is equal to 98.6 or that it's not. And then our second step is to establish a statistical decision rule, and that's setting our alpha rate. We want to do this before we look at the data so that we make sure that we're not being biased in any way. And the typical alpha value is 0.05, which means that we're willing to accept that there's a 5% chance that we may say that the null hypothesis is rejected, but it was actually true. The third step is to calculate our test statistic, and here's our formula for t, and we have the mean and the proposed population mean that's written up in our null hypotheses, and then we have our standard error of the mean. So we start with calculating the standard error. We know from the data that we have a sample size of 25. We know that x bar, this is the same data we used for calculating a confidence interval in an earlier module. So we have the mean is 98.524 degrees Fahrenheit, and our standard deviation that's estimated is 0.678. So we can use this information to then calculate our standard error. So 0.678 divided by the square root of 25, which is 0.678 divided by 5, which is equal to 0.136. So that's our estimate for our standard error. Now, when we're looking at our t-value, we need to have our mean from our sample, which is 98.524, minus the value for mu, which is from our null hypothesis, which is 98.600. Divide that by the standard error, which is 0.136. And when we calculate that, because our value from our sample is less than the one in the null hypothesis, it's going to end up being negative with a value of minus 0.56. So that is our t statistic that we've calculated. Now, one thing to note is that if there was a perfect match between the null hypothesis and the data, then our value that we would have calculated from our sample would be 98.6, and the whole value of t would be equal to 0. So now our value of t is not equal to 0, but is it significantly different from 0 enough to reject our null hypothesis? So the fourth step is to compare the test statistic with the decision rule and draw a statistical conclusion about our null hypothesis. So step 4 is that we need to compare our test statistic with the decision rule and draw a statistical conclusion about our null hypothesis. So in order to do that, we need to look at our decision rule, and we have to calculate our t critical value. We know that it's going to be a two-sided critical value because it could be both greater than our proposed value here or less than in order to reject the null hypothesis. And we need to know our degrees of freedom. Our degrees of freedom are n minus 1, which is going to be 25 minus 1, going to be equal to 24. And now we can look at our t-distribution table, and we need to look at our level of alpha for the two-tailed test. So alpha, we decided our critical value is 0.05 for our decision rule. And we're looking at a two-tailed test because our null hypothesis is that the population mean of mu is equal to 98.6 degrees Fahrenheit. So our alternative is that it could be either less than that or greater than that. So we're looking under alpha of 0.05. Our degrees of freedom is 24 over here. So we look down, and our critical value is 2.064. So we're looking for our t critical, and our t crit is equal to 2.064. A good way to look at the decision rules for deciding about our null hypothesis is to draw out the distribution. We have our t critical value of 2.064, and because this is a symmetrical distribution, on the other side we'll also have a critical value of negative 2.064. And remember that in the tails, if our value is greater than the critical value, that means that it's fallen in the region where there's 5% or less probability that the difference that we see is just due to random chance. So that would be in the tails. Our test statistic that we calculated has a value of minus 0.56. So this is our t statistic is equal to minus 0.56. And because that's in the middle region here and not out in the rejection region, we're going to retain our null hypothesis. So another way to write that would be that the absolute value of our t statistic is less than our absolute value of our critical, right? And I'm writing in absolute values because it's falling off to the left-hand side here, so it would be negative. Therefore, we retain our null hypothesis. And if we're asking the question of, did the sample come from a population with a mean or mu of 98.6 degrees Fahrenheit, the data suggests that yes. Given that our t statistic value is 0.56, there's one step further that we could do with this that isn't mentioned in the book, is to just look at the probability associated with getting that value. So here we have our degrees of freedom of 24, and notice that as we have an increase in our alpha, that the values of our t statistic drop, and our value for this example is minus 0.56, and it's less than this value of 1.318, which would mean that there's greater than a probability of 0.2 that the data actually come from the same distribution. So one other thing that we could write here is that, so the p-value, which is the probability that our data came from the same distribution is greater than 0.20. And that's just a little bit more detailed. Then we can write that the probability is greater than 0.05. Remember that if the probability is less than 0.05, only then we would say that there was a statistically significant difference.